Dear guests, let's move on. And if you wake me up in the night and ask me what do software engineers do, I will answer with they're developing frameworks and building storages. And the story behind it, the journey with the ups and downs, is always very interesting. So please let me welcome our next speaker, Ashot Vardanian from Unum Cloud, who will describe us his journey.
Hello. Thank you for inviting. So my talk is called Designing the Fastest Key Value Store, but I can never squeeze the content of the talk into the title, so I'm always bad with it. The part that I wanted to share is not just like what's it to design a key value store like this, but also the story of how we got to doing it. But before all of this, I guess it's rude not to introduce myself, at least to the people who don't know me yet. My full name is Ashot, short is Ash. I think I was programming since around 2003, and since then I've tried doing almost everything there is in the world of programming, from basic Olympiad questions to web, front-end, mobile development. I was in the first wave of iOS developers back in 2009 with iOS 4, when there was no automatic reference counting and memory management. Then I got into science, and in 2015 I started a project that I'm still doing until today. It's called Unum. I hope that I will spend the next 30 years of my life working on technologies as cool as the stuff that we design here. And potentially relevant to the conference, I currently live in Armenia for the last 2 years. I also organize the Armenia C++ community. We are about 700 developers now, very passionate about high performance. And we have a meetup a couple of days from now, so if you're still in the city, we'll be super happy to see you among our attendees or potentially speakers this time or next time. So in 2015, when I started working on Unum, I worked on a ton of different things, including custom neural network architectures, neural graph algorithms with lowered asymptotic complexity, analytics, both on CPU side and the GPU side. And when I say GPU, it's not just exclusively CUDA, it's also OpenCL, SYCL, Vulkan, all kinds of stuff. We had our own in-house custom encryption, compression, so a lot of free time for people to do stuff they really love. But for a long time, we had nothing in the form of a product or anything tangible in the open source. In today's talk, we'll show how this changed. So at some point, my daily routine would look more like this. So my homepage in the browser would have those 4 primary bookmarks with different kinds of intrinsics for Intel intrinsics, or more generally x86 CPUs, LLVM, CUDA, GCC. Some of them are compilers, some of them hardware specific. The point is, I was working on the kind of software that you see below. Intrinsics is like essentially a layer between C and assembly. So you think you're working in C, but you're designing platform-specific code. And I could spend a week working on something that runs, let's say, in 7 nanoseconds. And I would try to optimize it to work in 5 nanoseconds. From one perspective, you may not see it as a valuable form, a right form to spend time, because an engineer just spent 7 days, and the result is 2 nanoseconds gained. But once you multiply it to billions of machines all around the planet, it suddenly makes sense. Then I started packing all of these things together into various prototypes, and of course I had a part of storage. And this part of storage wasn't designed by us. We just took the industry standards like everyone else does. So Postgres, MongoDB, Neo4j, you name it. And of course, there were bottlenecks. If one part of your system is designed to optimize from 7 nanoseconds to 5 nanoseconds, and the best I/O devices are operating generally at tens of microseconds, and most of the I/O in those databases is not really asynchronous or advanced with a kernel bypass, you're going to have some problems. So last year, I wrote this article in our corporate blog on unum.cloud, the DBMS Gold Rush. It is about some of the other database alternatives that we could have used, but actually, like, we started working on our internal stuff even before this appeared. So this is the chart of how much money they raised last year versus how much money they've raised overall. All of them work on kind of different architectures of databases. Some of them are SQL, the others are NoSQL. Some of them are oriented for tabular data, others documents, the third one's graphs, but they have something in common. And it's not just the very fact that in the 1 year they've raised more than in their entire previous history. That's how hot the market is and how important it is to make data access more efficient. But more than that, almost all of them are built on the same technology. So the point is, in the past 40 years, the algorithms have advanced significantly, and even the open source frameworks are advancing, even though with a huge delay. But whenever you build a database, the most important piece of a persistent data structure that you need is a key value store. Essentially, it's an associative container where you map either a string or an integer to another binary string most of the time. And within those key value stores, the most famous one is RocksDB. It was started by Facebook, and you can see it as a spiritual successor to LevelDB by Google. Obviously implemented in C++, like most of the high-performance software today. It adds transactions. It's implemented as a log-structured merge tree to be better at write operations, let's say B-tree-based architectures. Facebook internally uses it to have their own flavor of MySQL, which they call it MyRocks. Within Twitter, they designed a distributed store that is also based on RocksDB. Yahoo has a store that's based on RocksDB. And half of the database companies that grow today are based either on RocksDB or something similar. So same for CockroachDB and Yugabyte. They both seem to be like a version of a distributed Postgres on top of RocksDB. And to be honest, I can name maybe another 10, 15 companies with the exactly same promise. And aside from this, there's also all kinds of message queues, and then protocols with some form of statefulness or persistency. Most of the time, it also goes into a persistent key value store like RocksDB. So I was coming from this high-performance computing world, and then I tried using RocksDB myself. It wasn't like last year, it was more like 3-4 years ago, but most of the things haven't changed within their code base. So when I look into it, there are some things that immediately pop into my eye. One of those things being the fact that, well, yes, you see dynamic polymorphism on every function call, like virtual functions. But aside from that, the library extensively uses standard template library containers, such as std strings and std vectors. And those things are generally templates. That's because it's a templates library. But they instantiate them specifically with one default allocator, which means if you're using this, your entire system will be using the same allocator, which is not a high-performance approach to do things. Another problem is that once you get into the most important function of all, multi-get, that will be doing batch read operations that would later go into all kinds of other databases, every function call will later produce 4 instantiations of vectors, every one coming with a heap allocation. So this is not really the kind of approach that we like. You can find the links to the headers in the bottom of the slide, so you can go back and see and compare what I mean. Next, I tried looking into the structure of the file, and I immediately see a lot of different blocks, including different probabilistic structures like Bloom filters. And whenever I see stuff like this, I just know this thing will not work well with parallel architectures. And if we're going to, let's say, combine together SIMD instructions, GPGPU stuff, and database I/O, having such complex files is not generally the way to go. And then you go further into the way they do I/O. So like, how does the top layer interact with this file structure? And all of a sudden that you realize that whatever requests come into the function have to be augmented with a lot of additional metadata. So within maybe like 3, 4, 5 layers of abstractions just within RocksDB, let alone the 10 layers of abstractions in the database that's built on top of it, every successive layer adds additional allocations, additional processing, and passes over this data with various not so efficient containers, even such as unordered sets. So just like a mediocre implementation of a hash set. We wanted to go beyond that, but to be honest, these problems do not stop at the RocksDB layer. It goes beyond into the Linux kernel as well. So once you start tracing I/O through every single line within the Linux kernel that will be passed, you will start noticing that most of the applications would go to through libc to user space buffers, then through page caches, then block layer I/O, and then the device layer. Within every layer, you have dozens of checks, lots of mutexes to synchronize access between different processes, different I/O operations targeting the same files. Oh, and I didn't even draw the file system layer within this diagram. So this diagram is not inclusive of all the complexities that will be done for every byte that you read from disk or write from disk. So we thought we need something for our internal I/O because our ambitions are always beyond our capacity for storage and compute. So we had to design something with our core principles, like absolute performance, and no matter how much time it will take to engineer it. So we spent the last couple of years working on this. So from my perspective, like a modern key value store that can later power almost any database for any kind of application has to have like 3 core components. One is a concurrent mem table. Another thing is a versioning or garbage collection abstraction. And the last one is I/O logic. So obviously, we are not squeezing a couple of years of R&D with previous 10 years of work in this industry into a 25-minute talk. So we'll just focus on one of those 3 parts. But I can briefly mention that, let's say, the go-to approach for the concurrent in-memory part of a database or a key-value store is to build something like a skip list. And most of those skip lists, they allocate again from hopefully a good allocator. Most of the time, if you take, let's say, gemmalog and the classical libcmalloc implementation, you will immediately see that the performance is varying drastically. So if you're using structures like this ones without engineering something really custom, you're kind of moving your problem from your side into the general purpose allocator, which is not the way we thought we should work. For garbage collections, we did something crazy as well. So we are accelerating essentially database or like persistent memory with operations on GPUs, mostly through CUDA. And we also do some stuff with seamed explicitly, not auto-vectorization. So this really sets us apart on write operations. But I/O logic is the topic we focus on today. And within this I/O thing, there's also a subtopic that we'll drop into. So those are the I/O options you have today. Most of the modern databases either implement the first one or the second, which are kind of 20 years old. There are a couple of database brands that try to use I/O Uring, but from our perspective, I/O Uring gives them a lot more than they generally harness. So the ability of this new Linux kernel interface, the I/O Uring for interruptless I/O and communication between your user space application and the kernel side is far higher, far greater than, let's say, RocksDB and other implementations are squeezing. Then there is Magnum I/O, which is a work of a great team at NVIDIA who tries to connect a couple of PCIe devices between each other, bypassing the CPUs, essentially transferring gigabytes and terabytes in our case of data from every SSD into the GPU memory or mapping it at least partially to process afterwards. But today I want to talk about the next gen stuff, SPDK. So SPDK is the storage performance development kit. I think its primary purpose, or the reason Intel invested heavily into designing stuff like this, is the fact that they've been working on 3D memory, 3D Expoint, the technology that they built together with Micron. And the problem is, if you're designing devices that have a 5 microsecond latency, which is an order of magnitude improvement over most modern NVMe devices, you need a software layer that can actually let you use this performance in your applications. So the Optane SSD I'm showing here in the picture is capable of 1.5 million random read operations and random write operations per second. This is faster than most SSDs on the planet. We mostly use similar SSDs, but with slightly higher latency, but with significantly larger capacities than what Intel produces. So you will see some of the real-world benchmarks on some of the most advanced hardware not even available on the cloud today. So SPDK Hello World application is notoriously long. It's about 500 lines. And if you're coming from a place like Python, where the Hello World is just one print, this is a bit of a milestone to implement something like this. There's something similar. SPDK reminds me of Vulkan. If any of you used to do graphics, I think the Hello World application in Vulkan that was being popularized was about 1,200 lines of code. So this is twice as short. But even the first point on how you should try implementing something like this is an immediate no to most of you guys. So like you need to have like root privileges on the machine to try the system until it's matures enough to get into like most of the container runtimes. Actually, it's happening January next year. So you have to probe NVMe devices manually. You have to unmount them essentially from the operating system and mount them within your user space program. So SPDK is a set of essentially user space drivers that you link statically into your application. And all of a sudden, it's just you who's managing the NVMe device. There's no one else. Linux isn't stopping in the way. So one of the issues is that with IOUring, for example, you get the IOUring and liburing. Liburing is a set of abstractions that helps you get some of the things done without getting into concurrency management. In SPDK, some of it is left to you. It's like a more low-level interface. And all of the memory buffers that you are trying to fetch, or in which you are trying to fetch the data, into which, have to be aligned to page sizes that are matching the page sizes of your SSDs. And aside from that, they also have to be on pinned addresses. So those things immediately sound like huge issues, but we kind of found ways how to work around all of them. So first thing, forget about the file system. You don't have the abstraction of a file, you just have bytes. So in our case, most of the SSDs are 8 terabyte SSDs. So you have 8 by 10 to the power 12 slots that you just decide how to address, so how to fill it with data. Another thing, you shouldn't be doing caching, at least not the one that the operating system provides. So most of the modern I/O, even in the databases, relies on maybe 10 layers of caches. So there is this flag with which you can open the files direct on Linux and POSIX-based system, which essentially implies that operating system doesn't have to do caching, you're just doing everything yourself. You should definitely use that thing. It's an added problem, because when you're starting reading directly, not from a cache, but from disk, you cannot read misaligned addresses again. So essentially, in the databases, everything is of a different size, especially if it's not OLAP, but OLTP, where like rows have different sizes. So if all of your rows are different size, and some of them are split in such a way that part is on one page on SSD and another one is on another page, every single one of your I/O operations has to be restructured so that it aligns or potentially reads more data than it actually needs to, just for the fact of alignment. So let's benchmark all of this. Let's understand why the fuss is around. So we have a lot of our hardware here in Armenia. Some of the coolest, crazy, state-of-the-art stuff combined into InfiniBand network on 200 gigabit fibers. Big part of our hardware is liquid-cooled, CPU, GPU-heavy instances. This one is single socket, so we get less NUMA artifacts during benchmarking. Every one of the SSDs is about 8 terabytes, capable of about 7 gigabytes per second worth of read throughput, and about 6 gigabytes per second worth of write throughput. And there is a 1 terabyte of RAM on this socket, theoretically capable of 204 gigabytes per second. But according to our benchmarks, especially in like final applications, even though it's one socket, it has internal NUMA-like node essentially. And there are about 4 of them, and the content will go through Infinity Fabric. So we couldn't squeeze more than 150, 160 gigabytes per second worth of throughput, even within memory. So if we take the utility, a Linux utility called FIO, and run on those SSDs, the classical interrupt-driven Unix I/O system calls like pread and prewrite will give you 50,000 IOPS per second, and those are random reads for one single SSD. If you're using something like POSIX AIO that's been around for many, many years, you can significantly improve this number. This is already huge, like 10 times faster. But again, single SSD performance improvements do not generally imply same results for multi-SSD setups, especially for the stuff that goes through many layers within Linux, because it will have to be synchronized. Let's take IOUring. With IOUring, we're capable of squeezing 869,000 operations per second on an average run, and those numbers do not treat them with absolute accuracy. This is the general logic that we use throughout the year, understanding which part of the systems require a certain amount of work. So with IOUring, we're capable of squeezing 5 million IOPS from 8 SSDs on one single machine. So there are a lot of even large companies whose entire traffic is at the order of 5 million operations per second. So you can handle all of single businesses' data and all of their workloads with just one single node. And then it gets even better. Because with SPTK, we've squeezed 1.2 million from every one of those SSDs, capable of 1.45 million operations per second, totaling at 9 million IOPS, and getting closer to 9 by 4. So in case of 4 kilobyte blocks, this will be 36 gigabytes per second of persistent I/O from 8 SSDs. And in modern systems, especially if you go dual socket with, let's say, AMD EPYC setups with 128 PCIe lanes on every socket, you can have 24 of those SSDs, essentially squeezing over 120 gigabytes per second worth of throughput. And I've just mentioned that the memory system bandwidth in real use cases is 150 gigabytes per second. So even if you just do a single copy of this data along the way, your persistent memory's I/O throughput will be bottlenecked by your memory system. That's how fast I/O is these days. Or at least it can be if you implement it properly. So with RocksDB, which is like the go-to solution for key value stores again, this entire system on 8 SSDs, oftentimes on our benchmark, squeezes 57,000 write operations per second, batch writes in random places. Our solution, our key value store, squeezes 320,000 operations per second. And those are as fresh, these numbers, as it gets. I asked the guys to actually repeat all the benchmarks, and those benchmarks takes multiple days to run on hundreds of thousands of dollars worth of machinery. So we were running it for the last few days and just finished yesterday evening. So 320,000 batch writes, 4.2 million batch reads. So this translates into about 16.8 gigabytes per second worth of bandwidth in your final application, whatever you decide to build on this key value store. And we are pretty sure we can double this number over the course of the next months or maybe a year. So the question is, how are you getting to use all of it? So for a very long time, I told you that we were focused on the internal technologies, and we just love doing this stuff for the sake of engineering. But it's also fun when people actually start using your technologies and get true real-life benefits, when they can analyze orders of magnitude more data than they ever thought before. And that was my idea and my goal 7 years ago when I started, and it feels like we're getting there. So this year, and today specifically, I'm announcing our first major open source thing. It's called UKV. You can find it in our GitHub repository, github.com/unumcloud/UKV. The idea is that within the computing industry, there was this standard called BLAS, basically linear algebra subroutines. And it was defined like 50, 60 years ago, originally implemented in languages like Fortran, C, and assembly. And this standard by itself was the foundation of the last 40, 50 years of revolution in computing. I've loved this standard. I've used it extensively. I've implemented some of its variants. And today, for example, every hardware vendor like GraphCore, Cerebras, NVIDIA, AMD, whenever they design new cool parallel chips, the first thing they design a BLAS implementation for this specific hardware, so that every person who uses the standard, the BLAS, can automatically get the benefits of the cool new hardware that's being designed throughout the industry. So this is the kind of standardization that has happened in the numerical world. It hasn't happened in the I/O world. We want to help change this, so we've designed a narrow C layer that is called UKV, Universal Keys and Values. And once you have a standard, it's very easy to design both implementations and solutions on top of it. So we've implemented multiple backends, not just our technology, but we took industry standard approaches and used them to actually have alternative reference implementations in case you don't want to try what we have. And then for front-end parts, we've also implemented higher-level bindings. And when I say higher-level bindings, it's not the same as like most of the SDKs for SQL databases. Like all they do, they pass a string from a user side to the server side. In our case, those are structured bindings. And in a second, I'll describe what it means. So with this UKV thing, you just have a few header files. Behind it can be whatever mess you think is possible. So this current design may look complex, but it's extremely modular. So at this point, we have multiple key value stores, multiple engines that you can plug in internally. Most of them are open source. So we have a UMEM, which is an in-memory key value store, which is just a concurrent associative container. We have RocksDB, which is the most used key value store these days. We have LevelDB, which is the simplest of all publicly available key value stores by its design. So its code base is the shortest of everything I've described here. and it's maintained by Google. And we also have our own key value store design, UDisk. Aside from this, we also implement different forms of data modalities, essentially forms of data that you would store in the database. So as every other database is built on a key value store, to be honest, that's not too much of a work to implement. So our implementation of tabular workloads and document databases is about 2,000 lines of relatively simple C++ code, mostly using open source libraries that people already know and love. And this by itself can be a replacement for something like MongoDB. So MongoDB is a JSON library for internal representation of documents, plus a wired target key value store. You can take our document implementation from here, you can take an already provided RooksDB solution, and all of a sudden this package, which is just a few thousand lines of code, is by itself a replacement of a billion-dollar company, or like the services that they provide. Other modalities that we work on is binary data. And this is fun because, well, I told you we bypass the file system. This means that we can do I/O in a database at speeds that most people do not even expect from object stores. So people would put, let's say, big files such as video files onto a disk, but not into a database. Well, because a video file is too big to put into a database. That's crazy. Why would everyone want to do it? But then once you start building large applications, especially multimodal ones, when you have image data, textual data, tables, and so on, you have 10 different APIs, all of them with different consistency guarantees. And whenever you write something and then you pass to the next step out of those 10, and something fails along the way, you start rolling back every one of the transactions in different systems. If you just put everything onto one single ACID guarantee transaction, then this problem is gone. This is kind of the stuff that we want from this solution for ourselves, and we'll be excited if others find it useful in those scenarios as well. Then there is graph data, which is super relevant because some of our other labs within the startup work on AI research, and I'm passionate about neurosymbolic computing and neurosymbolic representation. So we need both graph modality and vector search, so that we're capable of searching for key approximate nearest neighbors in high-dimensional vector spaces. We now kind of merged all of it into a very compact project. It's already available as an embedded key value store and as a standalone solution. We're now working on a distributed solution, and next year we'll add replication and sharding. So the C standard itself is relatively concise. Every function name, such as UKV write, has a matching structure that describes the form of the operation, such as UKV write T. And it's all filled with default arguments, so you can just provide whatever key and value you want to write. You can define it as in a transactional form or non-transactional. You can flush or not flush. But then, more importantly, we do strides, just like BLAS. And this is one of the things that most of the database guys kind of unfortunately missed. So in BLAS, we have this concept of strides to minimize the copies. So essentially, when you work with big matrices and you want to multiply a part of one matrix by another, you don't copy a part of a matrix into a new buffer and then pass it to the function call. You just pass the pointer to address within this matrix, and then define the step with which you have to walk along this matrix to multiply elements of it. So the big problem, or one of the big problem in the interfaces when we have these modern databases with OLTP versus OLAP solutions is that some of them are more targeted for, let's say, row major approach, and the others are column major, and same for the structures and the interfaces. Some of them SOA, others are AOS. Structure of arrays versus array of structures. So when you use strides, this all goes away. You just say, like, this is the first key that I want, and then if you have like array of structures, the step is the size of the structure. If you have a structure of arrays, the step is just the size of every scalar, every key that you have. So one single interface will work for both kind of databases. And then more importantly, well, we realized that not everyone prefers C or C++, so we want to make this technology approachable to everyone. And we started with Python, because that's the second most popular language within our company, except for the C-like group with C, C++, CUDA, and assembly. So we had implementations for Java and Golang, but if I'm completely honest, I would rather wait a little bit or just join the work and help us polish those solutions so that they are as good as the ones for C++ and Python. For Python, we're doing stuff that is called like structured bindings. So essentially, everyone knows what Python dictionary looks like. It's a very simple interface. You just give a key and you write something into it. And then everyone knows what pandas feels like. It's just like a normal interface to work with tables. And everyone knows what network X, or many people know what network X is. It's the most popular library for network science and graph processing. We thought we can design interfaces and bindings for our system that replicate all of those libraries. Moreover, aside from the SDKs that are structured bindings, we also try to implement some of the most important APIs. Unfortunately, I understand that within this community, SQL is a very important thing. We do not target this part as of now, but if you have a cool SQL implementation, you can probably try and attach it to the existing streaming interface. So you'll have like a streaming setup. We don't do GraphQL. We had the REST implementation, but we most importantly focus on RPC, remote procedure calls, and Aeroflight RPC. So for those who don't know, Apache Arrow is the fastest growing ecosystem of projects targeting data processing. They started by defining an in-memory format for columnar or like array-like data. And this structure, this format, got immediately adopted throughout the industry for both CPU and GPU processing. And all of a sudden, this project became like a family project in a sense that there is now the Parquet format that is also part of this ecosystem. They've designed Flight RPC as a protocol for communication. They also have a protocol for SQL-like databases. And more importantly, the community adoption of this thing is just tremendous. So there is DuckDB, ClickHouse, Ray, Spark, PyTorch, everyone supports them. We also support them, but what's cooler, all of our interfaces within UKV, even though those are C interfaces and Apache Arrow is more like a C++ framework, are designed in such a way that they can natively work with each other. So this is the first case of such a tight integration when every part of their format, such as the fact that when they work with strings, they pack them into tapes. And within those tapes, they need to pass offsets to the beginning of every string. So let's say you have n inputs in a batch, you will need n+1 offsets to know the length of the final object. With our system, like we can immediately understand this kind of data being passed into us and reinterpret it without any copy on our side. The beauty is that this performance, those zero copy things that I'm talking about the whole day, no allocations, and fast I/O, it can be accessible. So if the implementation is difficult and complicated, doesn't mean using it has to be hard. So on the left side is the interfaces that you generally expect from a Python dictionary. And if you pay attention, I have two similar function calls for every functionality, like assignment operator and the set function. So those are replicating Python 3 and Python 2 interfaces. So for example, hasKey function was removed from the Python standard in the Python 3, but it was present in the Python 2. And depending on what you like, you can use either one of them. More importantly, we support batch operations. And batch operations will work with lists, with tuples. They will work with arrow arrays. They will work with NumPy arrays. Essentially, anything you pass, we'll try to convert it into the best form that we can observe internally. Probably one of the last things that I'll mention is that I was talking about like pandas, network X, and how similar it can feel. Well, we're already getting there, but we are also adding some of the functionality that's not present, let's say, in pandas. For reference, the kind of sampling that we want to integrate. So when you work with pandas, you generally work with tables that are just thousands of rows. In our case, this same interface, even within a single machine, can reference a table that is 400 terabytes in size. And it's not just like two files that are 200 terabytes each. It's every row is maybe a couple of kilobytes, and beneath you have like 100 terabyte worth of those. So for, let's say, machine learning applications and a lot of other research that we do, it's relevant to have things such as sampling. But if those operations are not natively supported by your interface, you have to read all the keys that are present in the database, shuffle them, sample them, do whatever you want, and only then query the data. We've integrated some of those, let's say, AI age applications, or like AI age functionality into the database layer itself, so that we can support the rest of the research that we are doing and hopefully others are doing as well. So you can already try it. on our GitHub, there's the sources that you can now build with GCC mostly. We use CMake for the build system. Bindings for Python are generally built with PyBind, but we're researching faster alternative because PyBind by itself adds a layer in between. Aside from this, we are working towards MSVC builds and Apple Clang, which is a bit complicated, especially once you start dealing with large ecosystem projects like Apache Arrow, because it's like hundreds of libraries within one, and you have to find a way to build every one of them properly. Golang and Java bindings will be coming soon. And I'm not sure the Docker image is right now available on the Docker Hub, but it will probably be this weekend. So that's it. And the last potentially unrelated reminder is that there's the C++ group that we have here. And this is just one of many cool communities that exist in Armenia. We've had dozens of international conferences just this year alone. We have a huge, vibrant AI community, a lot of Java and C# developers as well. But if you ever come again, make sure to attend some of the other conferences and join our communities. And of course, the meetup that's happening 2 days from now. Thank you very much. Oh, so there's one thing that I had to say in the beginning, that the best questions will be getting awards and gifts from the organizers of the conference, so that you could prepare, remember your questions, and then ask me in the end. Well, it may have not been a fair fight in that case. So now we have the moment for questions, and the best one is still getting the award, right?
Yes. Thank you. Thank you for doing my job.
Okay.
So, do you have any questions here or online? Don't forget to rate the talk. There is a QR code for that, and another QR code to get access to our Telegram chat here and ask any questions. Any questions here? Well, I'll check.
Don't be shy.
Don't be shy.
I'm very friendly.
We have gifts for the questions. Don't be shy. If you're a lone soul with a question, you'll get a pair of socks to keep you warm during the nights. Yes, question to the left.
Can I ask a question from here? Yes. First of all, thank you very much for a great and interesting introduction. You have talked about the languages like Python, Java, Go, right, that work with data. What about the languages that, like Scala, right, that works with big data and deals with distributed RDDs, right? What about this tool as a language?
So we are very open to every language and every community to come and design bindings and interfaces for their cases. For the very beginning, we thought that it's wise to concentrate on like some of the core technologies. So like Scala, if I'm not mistaken, I never used it, still belongs to the JVM family, if I'm right? So having JNI bindings for Java native interface might be compatible with Scala as well, but obviously it may not be the same experience as writing a Scala interface directly. If you're an enthusiast, please be one of us, come join and contribute. We'll be happy to see everyone.
Thank you so much. The second question, you have talked about NoSQL, no structured data like images, videos, right? You have told that it doesn't make sense to put them into the database, right? Because of their huge size. Maybe I have missed that part. Can you just one more time tell the solution of this problem? And what about just converting them from JPEG format to bytes and etc.?
Oh, okay, sure. So JPEG format is still bytes. So like generally people split all the meme types into, or like file types into binary versus textual. JPEG is like one of the binary formats, just like any other, let's say, form of images, videos, etc. The issue there is not even the type per se, it's the size of the blob, like binary large object. If the ratio between the size of the key, which is oftentimes the path on disk or some unique identifier like 64 bits or 128 bits, compared to the size of the binary object is really large, oftentimes people prefer to use object stores or just directly file systems to dump files there. The problem being kind of related to what I was talking about here. If you have a database has to offer a lot of additional logic on top of just writing onto the disk. It checks for consistency, it reorganizes the operations, and to do so, it has layers of abstractions, every one of which requires a lot of careful engineering to avoid copies. So most of the time, copies happen of the data. And whenever you work with payloads that are, let's say, gigabytes in size, such as like a full HD video, the problem will be that going through like your interface down to the disk, those 4 gigabytes will be copied multiple times, and once they are saved on disk, then there will also happen a write amplification. Even though you may avoid trying to solve like, the write amplification problem, you can still avoid doing like the copies within the database layers if you just like do into the write into the file system and do not expect any consistency checks or stuff like that. You're welcome. One more in the front.
I have 2 questions. First question about NVMe. Can you open slide about
which one?
Format RocksDB and bad format for NVMe and not NVMe friendly. Yes.
Oh, you mean the file structure?
Yes, file structure.
Yeah, here you go.
Can you explain about NVMe friendly format? What's its format?
So that's a great question, actually. RocksDB has not one, but multiple formats. The one that I'm describing here, or literally a screenshot from their documentation, is the block-based table. So many, many years ago, when papers started appearing on alternative persistent key value store structures, people oftentimes suggested alternative layouts, because data layout is still important. No matter how many optimizations you do on top, there is still like the core part. Like, do you have to jump from one part of the disk to another, or are you just reading sequentially? So there is the blob format, for example. There's like the plain table format within RocksDB, but the block-based is structured in such a way that it generates files which will have .sst extension at the end if you're ever using RocksDB. Once you start looking inside, you will notice that it will have multiple data blocks in it. Data blocks can be structured in such a way that they are storing pairs of keys and values. So in case of RocksDB and some of the other key value stores, they are trying to solve like a case with string keys and string values. It is not a very efficient design, to be honest, because you're kind of solving the memory allocation problem, or like persistent memory allocation or resource allocation problem twice. It's like you need to be able to know like where the keys are and where the values are and how much space they are taking. In case of RocksDB and many other solutions, they are putting keys and values together into one continuous chunk. And then they have to put a lot of additional metadata about what kind of keys are stored within the data blocks, within some other functional blocks within the file. So you'll have blocks that are responsible for describing, let's say, ranges of deleted blocks. So instead of deleting the data within the file, they will just mark certain ranges as deleted ranges. Then they can have like something like a probabilistic data structure, like a Bloom filter, which may not be deterministically saying if a certain key is present in the file or not, but it may say that the key is definitely not present. So the way it will be structured is that within the log structured merge tree, you'll have multiple layers. The data from the in-memory part is dumped once in a while into the layer 0, where the freshmost data lives. But then within this layer 0, you do not have any guarantees that certain keys within files or key ranges do not overlap. Then every following layer, including layer 1 to layer n, has those guarantees that within the row of files, certain key only exists in one of the files. And then what will be happening is over time, as you're filling more and more data, these complex files will be unwrapped, processed, and merged together into older, longer chunks, living in the lower layers of the RocksDB. So if you're curious, I would suggest to go into their documentation. They have a website that is maybe not that easy for like documentation side, but on the RocksDB, they have a wiki section, and it has a lot of markdown files where you can read the details, including both the block-based table and the plain table.
Thank you. I have a second question. Can you open slide about PDK first? Yes. About root privileges and yes.
About what?
About root.
Throughput.
Root, yes. Not root, but root.
Oh,
root.
okay, yes.
Yes. I know SPDK, same as DPDK, have two drivers, user space IO and VFU. Do you research some latency and maybe throughput issue from VFU? VFU support to avoid root privileges, same issue. Do you research this?
Yes, so the SPDK project and all of the modern I/O is kind of in active development. So within every version, there's a slight chance. Well, first, there's performance improvement. Same with IO-Uring. Every new version of Linux kernel may bring, let's say, another 10% improvement to the speeds. So we always prefer newer kernels and newer versions of those libraries. As for SPDK, it's definitely, if you're using today, it's definitely better to run with root just because of the configuration mess. We're doing a lot of benchmarks, but not just not for the way you can set up this. We kind of try to align our development timeline with the timeline of SPDK's development, when you will be able to do those things without root privileges or within container runtimes, so that some of the coolest features that we have, I haven't even described them yet and haven't shown their numbers. But they will be coming once SPDK itself matures. And there, hopefully, we'll talk more not about like the performance of root versus not root or anything like that. I would prefer to concentrate on broader benchmarks for things such as NVMe over Fabric, when you have, let's say, arrays of hundreds NVMe, PCIe, Gen 4 or 5, hopefully, SSDs throughout your InfiniBand cluster, and you're connecting them to a single node. So your single node scales to petabytes of stored data at speeds that are unseen today.
Okay, thank you.
Any more questions? We have time to squeeze in at least one.
Hi. Hi, thank you for your presentation. I have a question about third point. Create multiply non-thread safe queues. Is it limitation of driver and SSD, or is it about hello world?
No. This is the general fact, I guess. So even with IO-Uring and lib-Uring, so let's say the IO-Uring counterpart will help you with memory mapping of shared memory between you and the kernel. And then if you're accessing this memory on your side, you will anyways have to do some form of synchronization so that the kernel doesn't corrupt your memory. Then once you have more threads on the user side, you also have to synchronize them. So similar with SPDKs, maybe even more so, because it's in a sense a lower level thing. It gives you the zero cost abstraction, assuming that implementing concurrency controls will anyways be expensive. And if you need them, if you're using something like this, it's expected that you know better how to synchronize your own accesses. So from our testing and the benchmarks that we do, we generally prefer to have, let's say, 3 threads or 3 queues, depending on the case, per NVMe SSD. With IO-Uring, we oftentimes saturate the capacity with 2 threads. So essentially, if you have 8 SSDs, you'd rather have, let's say, 24 threads working with them. If you have 24 SSDs, you should probably have how many? 72 threads. So that's a general thing, not just hello world.
Okay, so and the next question.
Sorry, we're short on time, unfortunately. You can always catch our speaker in the discussion hall later. So please, the best question asked up to this moment.
That is tricky. I think all the questions were nice. I would prefer to go with the one about the NVMe file structure, because that's one of the most eye-catching things that popped into me the first time I looked into the documentation. So that's the question I would have. Why would they have such a file structure?
So this gentleman in the first row. So thank you. Thank you, Ashot.